Alright, so we look at let's look at controlled rectifier. Alright, so now, okay, if you have a single diode like that, okay, connected to that load, we know that this will look like this, positive, 0, like that. What about if I want this to cut off, to chop off this? If I want it to look like that, okay, to decrease the average value, what do? I need to replace this with a thyristor. Right, so with a thyristor, now I can easily control the turn on. Remember that I said control turn on a semiconductor device, so I can control the turn on. All right, before this will turn on, there must be a signal. All right, so there should be a signal. So for me to get this being turned on, so now, if for instance I have, let's start like this again. So if I have this is our input there, right? Now, if I just put, let's say, I put a signal somewhere here. There's a signal here, and I leave this particular time before the signal. All right? So it means that this is going to take this amount of time. All right? In angle, we call that firing angle. So it will take that firing angle before it will start conducting. So that at the end of the day, you will get something that now looks like that. Okay, on reverse bias, this will block out, so you get another one again like that. All right, so you have something like this. So it means if I put a rectifier, a control rectifier, a rectifier here, replace that the diodes with the rectifier, so this can then change. So this will now look like, so instead of looking like that, all right, depending on the firing angle, so we can have, let's say like this. This is now the firing angle. Okay, so that is that firing angle. Okay, so this will be the DC output, how it will look like. All right, so that is so what we have here. So this is what we have here. So you have your, depending on the firing angle, if it's at 90, so you get this being chopped off at the center. If this angle is 90, it will chop off at this center, right? Remember that from here to here is 180 degrees, so this is 90 degrees. So if the firing angle is 90 degrees, this will chop off at this point. If the firing angle is 0, okay, then you have full waveform like that. Okay. So now if you now see the waveforms, what we got here is when the firing angle is 90, and then you check, this is when the when the firing angle is 0. So if firing angle is 0, then we have our normal full wave. Okay, and then when firing angle is 45, right? So you see that. So now let's now look at how we can derive the equation for VDC and VRMS. Okay. So How do we get the VRMS of this? As I said, from here to here, for a full waveform, we have this and that, which is 2 pi. So if you like, you can just get the average value of this. Okay. So how do we get the average value of that? So you just follow the same thing that we did before. You say that VDC is 1 over from here to here, the integral. Now in this case, it's now from this point to that point, right? Which is from alpha to theta to pi of this waveform. This waveform is still a sine wave. Okay, still Vm sine omega t dt. So this you can integrate. Remember, if you want to do it the way I said before, you can say, okay, 1 over 2 pi, all right, but you integrate from alpha to this multiplied by 2. If you multiply by 2, that 2 will still cancel the 2 here, so you still have 1 over pi. All right, so have 1 over pi, integral of that to that. And when you integrate sine, you get minus cos. Okay, so have minus cos omega t from alpha to pi. This is Vm is here, and this is 1 over pi is there. So you can easily evaluate by putting this value there. So you have 1 over pi Vm into minus cos pi minus cos alpha. Okay, did you get that? So, and what is cos pi? We said us then take coffee. Right, also take coffee. Pi is 180. So that means there is going to be -1. So we're going to have this Vm over pi into minus 1 minus cos alpha. Okay, I don't know what alpha is. Right, so now this is now plus and this is plus. So that means we have 1 plus cos alpha into Vm over pi. So VDC is 1 Vm over pi into 1 plus cos alpha. So that if cos alpha is 0, if alpha is 0, then cos 0 will be 1, and 1 plus 1 is 2. It becomes 2 Vm over pi, which is our original equation for that, right? 2 Vm over pi. All right, so for a control rectifier, all right, we can use VDC is Vm over pi into 1 plus cos alpha. Remember, you might be asked to derive that, okay? So now we can also calculate the VRMS, all right? Just follow what we did last time to calculate the VRMS or to derive the VRMS. So VRMS is a root of this mean, which is 1 over pi integral of 0 to pi of Vm sine omega t, this mean. So root mean squared, like that. Okay. So, but this will now be from, put 0 to pi, it should be from alpha to pi. So you just do the same thing that we did before. So here, so you have the square root of 1 over pi of Vm remember that this Vm is squared, Vm squared over pi. Now sine squared omega t dt. Now sine squared omega t is the same thing as half into 1 minus cos 2 omega t. Okay, so we can have this as the square root of Vm squared over pi into half by 1 minus cos half by 1 minus cos 2 omega t integral alpha to pi. I forgot to put integral again here. Alpha to pi, now the omega t. So that from here we can have this. As Vm squared over 2 pi. Remember, it's a square root. Okay. Into, when you integrate that, you get omega t, minus when you integrate this, you get sine. Okay, so you get sine 2 omega t over 2 alpha to pi. All right, you get that? So, and that's all. So we can evaluate. You can just put our values there. So you can just put our values. So this is Vrms being the same thing as the square root of V peak squared over 2 pi now into, so I'm going to put pi there. We'll have pi minus sine 2 pi over 2. So this minus alpha minus sine 2 alpha over 2, like that. Okay. All right, so we get something like that. Then we just need to open up the bracket. This is sine, so which will give you Vrms as the square root of Vm squared over 2 pi. Now, what is sine pi here? Remember, this is sine 2 pi is sine 0. Okay, so this will be out, that will be 0. So we left with pi there, minus, this is now alpha, okay, minus sine 2 alpha over 2. Okay, sine 2 alpha over 2. So this can give you V squared over 2 pi. V squared over 2 pi. Alright, by that. So we have right. So I think that's all about that. So you can just write this in a better way. You can bring out. Remember that 2 is the same thing as root 2 squared. Right. So even if I put root 2 squared here, it will be Vm over root 2 all squared And the square root of that can come out so that you have Vm over root 2 now into the here pi minus alpha minus sine 2 alpha over 2. Okay, so 1 over pi here. So this becomes that. That is what you need to know. So it's Vm over root 2 into 1 over pi, okay, by pi minus alpha minus sine 2 alpha over 2. Okay, so let's look at our equation. Remember that the rest of equations are the same for diode rectifier. All the equations in terms of TUF, the efficiency, form factor, and the rest. So look at this equation. We have a controlled rectifier which has 10 ohms with 230 volts, 50 hertz. The firing angle is 60. You are asked to calculate IDC, IRMS for the load, the supply current, RMS and the DC current through the thyristor, and also calculate the input power factor. So just do the same thing. Remember that VDC we have derived it to be Vm over pi into 1 plus cos alpha. So just substitute where your Vm is root 2 times 230, which is 325.27. So you just get 325.27 over pi into 1 plus cos 60, because our alpha, our angle, firing angle is 60. So if you substitute, you get 155.3. So the rest to calculate IDC is VDC over R, which is 155.3 over 10. And then also calculate, for us to calculate the IRMS for the load, I just need to get the VRMS so that I can divide VRMS by the resistance to get IRMS. So and VRMS from the equation we derived is V peak over root 2 multiplied by the square root of 1 over pi into pi minus alpha plus sine 2 alpha over 2. And V peak is calculated, that is 325.27, so we divide that by root 2. Remember we calculated the V peak here, we'll multiply 230 by root 2. So now when we substitute, you will get VRMS to be 206.3. Okay, so now we can calculate therefore IRMS, which is VRMS over R, that is 206.6, 0.3 divided by the resistance, which is given to us, okay, which we calculated, is given to us as 10 ohms. So once you divide 206.3 divided by 10, will give you 20.63. And IS, the source current, is same as RMS output, which is 20.63. The thyristor diode current, the thyristor current is IDC over 2, and the RMS of the current flowing through the thyristor is IRMS over root 2. Okay, you got that? You can also calculate the power factor, which is PSC over VSIS, where PSC is V RMS over R, or you can just write IRMS VRMS. Okay, then divide by VSIS. So in this case, the VO RMS is 206.3 divided by 10. Okay, then over 230 by 20.6. you can now see the difference between controlled rectifier and controlled rectifier and uncontrolled. For uncontrolled, this VS here is VRMS here. But once you have controlled, now the VS here and the VRMS are not the same, because the VRMS will use this equation. But if it is uncontrolled, the VRMS here is V peak over root 2, which is the same thing as input voltage. Okay, and that is why when you look at this power factor, it's not 1 in this case. All right, so we have that to be 0.897. Right, so you got that. Now, also with a highly inductive load, if you have a controlled rectifier with highly inductive load, you can see how the waveform will look like. Normally, once the alpha, the final angle is 0, okay, the waveforms, as we said before, the voltage will look like that of a normal uncontrolled rectifier. That is the use of diode. But immediately you change the final angle, okay, now let's say to 60, right? So this is now, because of the inductance, this is now how the signal will look like. Okay, so there's going to be a path on the voltage that goes to the negative side, all right? And you can see the current is ripple free, just like a straight line. So the same thing when the angle is 90 degrees. Now, so if you have a highly inductive load, all right, so we're going to have the VDC to be 2 Vm over pi cos alpha. Okay, this is for highly inductive load. If it's not highly inductive load, we know that our VDC still remains 1 plus cos alpha, or multiplied by Vm over pi, all right? And then you can see how the source current, Is, is not sinusoidal anymore. It looks, contains a lot of harmonics with flat tops. The same thing with that of transistor. Okay, so you should know those waveforms. Okay, so for control rectifier with highly inductive load, we now see that VRMS is V peak over root 2 when the inductive load, when you have a highly inductive load. So you should know that it means that VRMS, or the source current voltage, becomes the RMS voltage of the output. Let's look at this example here. It's 1,800 watts, 150 volts DC connected to a control rectifier via a 230 volts AC supply, assuming ripple-free motor current. Calculate the following. Remember that a motor is an inductive load. So I have to calculate the firing angle, calculate IDC for motor, calculate VRMS for the motor, calculate DC current through one thyristor, and also apparent power of the transformer. Now, one thing you should know is that the DC motor is highly inductive. Okay, so for a highly inductive load, VDC is 2 Vm over cos theta. Please don't get confused with this equation. Let's go back to the one we derived before. if you check here, this is for normal resistive load, where VDC is Vm over pi into 1 plus cos alpha. And also VRMS is Vm over 2 pi, over the square root of 2 multiplied by the root of 1 over pi into pi minus alpha plus sine 2 alpha over 2. This is for normal resistive load. Okay, but for highly inductive load, right, you can, the theta, you are going to have 2 Vm over pi cos alpha as VDC. And also you are going to have that Vrms is V peak over root 2, which is just the same thing as the source voltage. So in this case, this question, so they ask us to calculate fine angle. So you just need to write that 2 Vm over pi cos alpha is VDC. So we have to make alpha the subject formula, which will give you the arc cos of VDC pi over 2 Vm, where VDC is given to us because from the equation you have 150 volts DC. So 150 times pi over 2 times Vm. Vm is root 2 times 220. The source voltage is 220. So we get that. So arc cos of that will give you 40.77. And the next is to calculate IDC. So if I know the power, the PDC, which is 1,800, and I know the voltage as 150, so I know that power is IV, or I squared R. But since I know V already, so we can just say IDC is P over V, which is 1,800 over 150. That is 12 amps, ripple free. And then VRMS is the same thing as the source voltage. Remember that this is the same only if it is highly, high inductive load, like your motor. If it is resistive load, then it's different. VS cannot be VRMS. All right. Then the current through the transistor, DC, is IDC over 2. You just look for the IDC we calculated before, the 12 amps divided by 2, to give you 6 amps. Okay, so now also the power of the transformer, or the source power, VSIS, where IS is IDC for ripple free, highly inductive load. So we can multiply 220 by 12 to give you 2,640 volt amperes. Okay, you get that? Now, the next thing again is let's look at some other special converters. All right, so now let's look at semi-converter or half-wave rectifier. If you check the drawing, you see the difference between what we had before and what you can see now. It's just a mixture of diode and transistors. Okay, so if I have 4 diodes like that, right here you have 4 diodes. So if I make maybe this one and that to be a thyristor, that's a semi-converter. Now it's no more diode all through. You have these 2 diodes and this one thyristors. Or I make these 2, okay, these 2 thyristors, or this one diode. Then that's what we call semi-converter. All right, so you should know how to sketch that. All right, so have a semi-converter. So the waveforms and equations the same as for control rectifier with a load. Now, this is now semi-converter. If you have a highly inductive load, all right, in this case, with inductive load, so we can have the waveforms, which is a little bit different, and the current, source current, will be different also. If you want to calculate the source current for a semi-converter highly inductive load, IS will be the square root of pi minus alpha over pi multiplied by IRMS. I through the transistor, will be alpha minus pi over 2 pi multiplied by IDC. And the IT RMS will be the square root of pi minus alpha over 2 pi multiplied by IRMS. So you should know the difference between the semi-converter and the normal converter. So we see that once you have a semi-converter like this with highly inductive load, now the I input RMS is no more the same as I output RMS. So we rather use this equation that I input RMS, that is your IS, is the same thing as the square root of pi minus alpha over pi multiplied by IRMS. Okay. Let's look at an example. A semi-converter has a 10 ohms with 230 volts supply, 50 Hz. The firing angle is 60. We are asked to calculate IDC, IRMS, supply current, RMS and DC current through one thyristor and input power factor. So remember that IDC is VDC over R. So I just to get VDC, and VDC is VM over pi into 1 plus cos alpha divided by, that will give you VM is 325.27, that is root 2 times 230. So divide by pi, then into 1 plus cos 60, that gives you 155.3. So IDC becomes VDC over R, which is 155.3 over 10. Now, the VRMS, as we said before, will remain the same as VM over root 2 into the square root of 1 over pi by pi minus alpha plus sine 2 alpha over 2. So which when you substitute, you will get 206.3. So IRMS will be VRMS over R, which is 206.3 over 10, giving you 20.6. And then IS is IRMS, which is 20.63. IDC is I transformer DC, or I thyristor DC is IDC over 2, and the RMS of it is IRMS over root 2. So you get that. Then you can also calculate the power factor, okay, PSC over VSIS. Now, let's now look at something a little bit different. If you check this question, it's a 1800 watts, 150 volts DC connected to a semi-converter. Now, this DC motor, which means it's a highly inductive load. So, and the semi-converter via a 230 volts AC, assuming ripple-free motor current, calculate the firing angle, IDC for motor, VRMS for motor, DC current through one diode thyristor, apparent power of the transformer. So VDC, we also calculate the firing angle. We just need to calculate VDC. And VDC is the same thing as VM over pi plus 1 plus cos alpha, where VM is root 2 by 220 which is 311.1 volts. So, because alpha will now be VDC pi over Vm minus 1. You just make that a subject, and then from there you will get that alpha is 59.02, which you can convert to radians. Now, so the next is to calculate IDC, which is power over voltage, which is 1800 over 50, ripple-free IDC. Now, for you to calculate the VRMS of the motor, so we still use the normal equation. VRMS is Vm over 2 by the square root of 1 over pi into pi minus alpha plus sine 2 alpha over 2. Now the question is, how did we get 1.03 for the alpha? So you just need to know that, should know that 2 pi radians is in radians is equals to 360 degrees. Equals to 360 degrees. And right, so now remember that 2 pi radians is 360 degrees. So if I have if you are given an angle of 59.02, 59.02, so you just cross multiply, what will it be? So it will be 59.02 times 2 times pi, and then divide 360, you get 1.03. So 1.03. Okay, that's how you can convert angle to radian. Right. So once you do that, so you are going to have the VRMS to be V over root 2 into the square root of 1 over pi by pi minus alpha plus sine 2 alpha over 2. So you leave pi as it is, but convert the alpha, the outside alpha to radians, that's 1.03. Okay. Now the inside, the sine 2 into 1.03, you may not put that there. Right, what you do is you just write it as it is. So you can write like this, that sine 2 into 59.02. Just make sure this is in degrees, except if you want to convert, if you want to put your calculator in radians, okay? So this will be 1.03, and minus here, pi, then 1.1 over pi. And here is Vm over 2. So I was just saying, this should remain as it is, pi, 1.03. You leave it as it is now in radians. You can just leave this as it is here, 5.09 times 2. You look for sine of it, divided by 2. As far as your calculator is in degrees. Okay? So, right, did you get that? So from there you will get 198.3. Then D, the transistor current, is pi minus alpha over 2 pi IDC, which is 4.033 amps. Then apparent power input, okay, is VSIS, where IS is pi minus alpha, the square root of that, the square root of pi minus alpha over pi, then multiply by IDC. So you get 9.839. So you can now from here get your apparent power input as 2164.36 VA. All right, did you get that? Please take your time and go go through the videos and solve the problems again.